Lecture 9.2, Day 2, Finding Common Maclaurin Series. Here we have a shot of the Liberty Bell in Philadelphia, Pennsylvania. We see part of Independence Hall on the left. Since this photo was taken, the Liberty Bell has been moved to a newer visitor center shown under construction to the right of the Liberty Bell. There are some Maclaurin series that occur often enough that they should be memorized. They are on your formula sheet, but today we're going to look at where they come from. The Maclaurin series generated by f at x equals 0, also known as the Taylor series at x equals 0, is p of x equals f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus etc. equals the summation from n equals 0 to infinity of the nth derivative evaluated at 0 over n factorial times x to the n. We'll start with a simple one as an example. 1 over 1 minus x equals 1 minus x to the negative 1. We list the function and its derivatives. We have 1 minus x to the negative 1, bringing the exponent down, decreasing it by 1, and using the chain rule, we get 1 minus x to the negative 2. The next derivative is 2 times 1 minus x to the negative 3. Then 6 times 1 minus x to the negative 4. And 24 times 1 minus x to the negative 5. Now we evaluate this column for x equals 0. We get 1, 1, 2, 6, which is 3 factorial, and 24, which is 4 factorial. Putting these coefficients into our series, we get 1 over 1 minus x equals 1 plus 1x plus 2 over 2 factorial x squared plus 3 factorial over 3 factorial x to the third plus 4 factorial over 4 factorial x to the fourth, which simplifies to 1 over 1 minus x equals 1 plus x squared plus x cubed plus ... equals the summation from n equals 0 to infinity of x to the n, where the absolute value of x is less than 1. This is a geometric series with a, the first term, equal 1, and r, the common ratio, equal x. We could generate this same series for 1 over 1 minus x with polynomial long division. We have 1 divided by 1 minus x. So just to refresh your memory on polynomial long division, we ask ourselves, what do we have to multiply 1 by to get 1? And the answer is 1. So we put a 1 on top, and we multiply 1 times 1 minus x. When we subtract, we get x. Then we ask, what do we have to multiply 1 by to get x? And the answer is x. So we put x on the top, multiply times 1 minus x to get x minus x squared, subtract, and get x squared. We continue this process, and we get x squared on the top, and then x cubed, and we could keep going, but we see the pattern. So we have a surprise use for polynomial long division, sort of a bonus for this lecture. Now for the fraction 1 over 1 plus x, we repeat our process. We have the function and its derivatives. Then we evaluate the function and its derivatives at x equals 0. We get 1, negative 1, 2, negative 6, which is negative 3 factorial, and 24, which is 4 factorial. We put those coefficients into our series and simplify. So we get 1 over 1 plus x equals 1 minus x plus x squared minus x cubed plus ... equals the summation from n equals 0 to infinity of negative 1 to the n times x to the n, where the absolute value of x is less than 1. This is a geometric series with first term a equals 1 and common ratio r equals negative x. We wouldn't expect to use the previous two series to evaluate the functions, since we can evaluate the functions directly. They do help to explain where the formula for the sum of an infinite geometric series comes from. We will find other uses for these series as well. A more impressive use of Taylor series is to evaluate transcendental functions. For cosine x, we list the function and its derivatives, cosine x, negative sine x, negative cosine x, sine x, cosine x. Then we evaluate this column for x equals 0. We get 1, 0, negative 1, 0, and 1. Inserting these coefficients into our standard form, we get cosine x equals 1 plus 0x plus negative 1 over 2 factorial x squared plus 0 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth. Every other term, the ones with 0 coefficients, cancels out, giving us cosine x equals 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6 over 6 factorial equals the summation from n equals 0 to infinity of negative 1 to the n times x to the 2n over 2n factorial. Both sides are even functions. And cosine 0 equals 1 for both sides. This could help you remember the formula. For sin x, we repeat the process. We have sin x, cosine x, negative sin x, negative cosine x, and sin x. Evaluating for x equals 0, we get 0, 1, 0, negative 1, 0. Our series becomes sin x equals 0 plus 1x plus 0 over 2 factorial x squared plus negative 1 over 3 factorial x cubed plus 0 over 4 factorial x to the fourth, etc. Once again, every other term cancels out, and we get sin x equals x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial equals the summation from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial. This time we notice that both sides are odd functions, and we notice that sin 0 equals 0 for both sides. Once again, this might be a help in remembering the formula. For 1 over 1 plus x squared, if we start with this function, 1 over 1 plus x, and substitute x squared for x, we get 1 over 1 plus x squared equals 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth, etc. This is a geometric series with first term a equals 1 and common ratio r equals negative x squared. If we integrate both sides, we get inverse tangent x equals x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7 equals the summation from n equals 0 to infinity of negative 1 to the n times x to the 2n plus 1 over 2n plus 1, where the absolute value of x is less than or equal to 1. This looks the same as the series for sin x, but without the factorials. Consider the natural log of 1 plus x. We list the function and the first few derivatives. So we have ln 1 plus x, 1 plus x to the negative 1, negative 1 plus x to the negative 2, 2 times 1 plus x to the negative 3, and negative 6 times 1 plus x to the negative 4. We substitute 0 in for x and evaluate. We get ln 1, which is 0, 1, negative 1, 2, and negative 6, which is 3 factorial. Using these values in the formula for the Maclaurin series, we get ln 1 plus x equals 0 plus 1x plus negative 1 x squared over 2 factorial plus 2x cubed over 3 factorial plus negative 3 factorial x to the fourth over 4 factorial. Simplifying, we get 1 plus x equals x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4. And it's not difficult to find the general term, so we have the summation from n equals 1 to infinity of negative 1 to the n minus 1 times x to the n over n. Notice that this is an alternating series. For what values of x will this series converge? In a few days, we will learn a more formal way to find where the series converges, but for now, we will try a few points. At x equals negative 1, we have ln 1 minus 1 equals negative 1 minus negative 1 squared over 2 plus negative 1 cubed over 3 minus negative 1 to the fourth over 4, which equals the summation of n equals 1 to infinity of negative 1 to the n minus 1 times negative 1 to the n over n. Simplifying, we get ln 0 equals negative 1 minus 1 half minus 1/3 minus 1/4 equals the summation from n equals 1 to infinity of negative 1 over n. This diverges since the natural log of 0 is undefined. As we see on the graph, if we approach from the right-hand side, the limit approaches negative infinity. So for our original series, x must be greater than negative 1. If we factor out a negative 1 from our formula, the remaining series diverges to infinity. It is called the harmonic series. If we try x equals 1, we get ln 1 plus 1 equals 1 minus 1 squared over 2 plus 1 cubed over 3 minus 1 to the fourth over 4, which is equal to the summation of n equals 1 to infinity, negative 1 to the n minus 1, 1 to the n over n, which simplifies to the natural log of 2 equals 1 minus 1 half plus 1/3 minus 1/4, which is equal to the summation from n equals 1 to infinity of negative 1 to the n minus 1 times 1 over n. This series converges because each term brings our sum a little bit closer to a limiting value. This is called the alternating harmonic series. It is usually written 1 minus 1 half plus 1/3 minus 1/4 equals the summation from n equals 1 to infinity of negative 1 to the n minus 1 times 1 over n. I might add that if you're not convinced that this series converges, we will learn in a few days a rule for convergent alternating series, which will convince you. If x is any number greater than 1, the numerator is an exponential function while the denominator is a linear function. The numerator will eventually grow faster than the denominator, so the terms do not approach 0. the partial sum eventually moves further from any limiting value. The following slide shows the first 60 partial sums for this series if x equals 1.1. We see that at first the sums appear to approach a limit, but after a certain point they get further and further apart. To summarize this series, ln1 plus x equals x minus x squared over 2 plus x cubed over 3 minus x to the fourth over 4 and so forth, which is equal to the summation from n equals 1 to infinity of negative 1 to the n minus 1 times x to the n over n. And the interval of convergence is negative 1 is less than x, which is less than or equal to 1. The harmonic series is 1 plus 1/2 plus 1/3 plus 1/4, or the summation from n equals 1 to infinity of 1 over n, and it diverges. The alternating harmonic series is 1 minus 1/2 plus 1/3 minus 1/4, which is equal to the summation from n equals 1 to infinity of negative 1 to the n plus 1 times 1 over n, and it converges to ln2. We have saved the best for last. Consider e to the x. The original function and every derivative is e to the x. And if we substitute 0 for x, we get e to the 0 or 1 every time. Substituting into the formula for the Maclaurin series, we get e to the x equals 1 plus 1x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth. Simplifying, we have e to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc., which is equal to the summation from n equals 0 to infinity of x to the n over n factorial. When x equals 1, we get the reciprocal of factorials series, which converges to e. So the summation from n equals 0 to infinity of 1 over n factorial equals e.